Good evening, everyone. Welcome to the sorry. So, good evening, everyone. Welcome to the week 7 live interaction session for the course Waste to Energy Conversion. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. So, I think we can start our session for today. So, let me just share my screen. I hope my presentation is visible and I'm audible. Okay, so let's start our session for today. So, welcome everyone to the week 7 live interaction session of the course Waste to Energy Conversion. This course is offered by Professor Prasenjit Mondal sir from the Department of Chemical Engineering IIT Roorkee under the NPTEL SWAYAM program. Myself Pratyumnan, a PhD research scholar from the Department of Chemical Engineering IIT Guwahati, Assam. So we have been meeting each other for almost 6 live interaction sessions. So I conduct live interaction session for this course waste to energy conversion for the Jan to May 2026 semester. So we have been meeting for 6 weeks and today is the seventh week. So we have traveled so far in this course and we have actually learned about how to convert waste to energy through different means. So initially we discussed about the thermal conversion routes. So where we discussed about three different types of routes, or you can say three types of classification within the thermal route, which is the pyrolysis. After pyrolysis we go for gasification and then we come with combustion. Or you can also say that first we discussed about combustion or incineration, then gasification, and then pyrolysis. So all these three methods, as we have discussed several times in the live interaction session as well as in the course, that Just a second, 1 minute. So, where we discussed that as the concentration, or you can say that with respect to the ratio between the oxidant to that of the fuel, we classify these three processes as pyrolysis, combustion, and gasification. So after that, we actually moved on towards discussing about the energy production from the plastic waste. And in the last live interaction session, we discussed on the concept of energy production through anaerobic digestion and on the microbial fuel cell. So I hope everybody is able to recollect, and we also had quite a extensive discussion on the microbial fuel cell part, and we also discussed about the different types of factors that affect the efficiency of the fuel cell. So just to before starting, could anyone tell me some of the factors that usually affect the microbial fuel cell, or you can say the energy the efficiency of the microbial fuel cell, the factors affecting the efficiency of the microbial fuel cell? Anyone? Yes, anyone? The factors that affect the microbial fuel cells efficiency. Any two or three factors? So typically you can say factors like the type of oxidant that you use in the anode chamber affects the efficiency of the fuel cell. Then you can also talk about the type of catalyst that you use also affect the efficiency of the fuel cell. The major reason being is that if you see in case of the cathode, where your oxygen and then the H plus ions as well as the electrons react, that particular reaction kinetics is very sluggish. What I mean by sluggish is that reaction is actually very slow. So in order to improve the rate of reaction, we use catalyst. So depending upon the type of catalyst that we use, the reaction kinetics can be altered. So that again affects the performance of your fuel cell. So type of oxidant, catalyst. When I say catalyst, both the amount of catalyst deposition as well as the type of catalyst that you use. Then later any other parameters that you can think of. Anyone? So types of microbes that you use in case of MFCs, microbial fuel cells, the type of microbes that you use in the anode chamber can also affect the efficiency of your fuel cell. Again, there are multiple different components, and as I said, each component is a field of study. So if you take up or if you happen to Google about fuel cells, you can easily understand that each and every component that forms the fuel cell is indeed a subject of study, and there are lots of research work on each and every particular component within the fuel cell. There are research on there is a great deal of interest in the electrodes that is used. There is a great deal of interest in the membranes that is used for the fuel cell, and then the type of catalyst that is used for the fuel cell. And there are also multiple groups who study how to improve the efficiency of the fuel cell when you have multiple fuel cells stacked in the form of uh, uh, when you stack all the fuel cells together, how the efficiency comes out. Because with one particular fuel cell you cannot actually meet the energy requirement for powering a vehicle. So how to stack multiple fuel cells so that we can enhance the energy as well as the power density of the system, that is again another major interest of study. Uh, so that's just I wanted to emphasize here once again. So after that we actually move towards energy production from fermentation, and that would be the topic that we will be continuing in today's live interaction session. And we will also continue on understanding how energy production happens through transesterification reactions as well. So in the last live interaction session we saw that using glucose we can actually obtain ethanol through fermentation process, and that ethanol is what is going to be used as a biodiesel. So we also saw that ethanol as such, if you use it in biodiesel, it does not have that much amount of calorific value. So we always try to blend it with the gasoline in certain fractions so that the energy density of the biodiesel as a whole can be improved. And the major reason for replacing gasoline with the biodiesel is because gasoline is not environment friendly. It is known to produce toxic emissions, whereas ethanol, on the other hand, is environment friendly. But since it lacks the energy density, or it cannot produce that much amount of energy, you actually try to blend it with the gasoline so that both the energy density parameter as well as the environmental friendliness are maintained within the system. So we also discussed about how from a starchy or a starch biomass you can actually get anhydrous ethanol. So I hope all of you are able to recollect the process. It's a four-step process. You take the starch or the biomass, then you do some sort of pre-treatment. Once that pre-treatment is done, you basically subject that biomass through fermentation process, and then you get ethanol. This ethanol mixture, it's actually a mixture, undergoes distillation. Once the distillation process is done and you get ethanol, that ethanol undergoes, there is a particular process. What's the process name? After distillation, what is exactly the process name? Anyone? Dehydration, right? So after you get the ethanol, you tend the ethanol is dehydrated so that you can produce anhydrous ethanol. So this is what we discussed for till the last live interaction session. In today's we will discuss more on this fermentation process. So previously the discussion that we had was for only the glucose and for the starchy biomass phase. Today we will discuss more on the lignocellulosic biomass, and how we can obtain uh, ethanol from these lignocellulosic biomass. So, when we talk about the lignocellulosic biomass process, especially in the distillation process, we have two types of distillation. One is the azeotropic distillation and another one is extractive distillation process. So, how many of you know what's an azeotropic distillation, or how many of you have an understanding on what's an azeotrope? What is an azeotrope? Anyone? What is an azeotrope? So, azeotrope is nothing but azeotropic mixture is nothing but it's a azeotropic mixture is nothing but it's a mixture of two solvents which has almost similar boiling points. So I hope everybody now has somewhat some can recollect what's an azeotrope. Almost all of us know what's an azeotrope. Just in case if you have forgotten, azeotrope is nothing but it's basically a mixture of two solvents where both the solvents typically have similar boiling points. So in that case, what actually happens is concentrating one particular or separating one of the solvent from that mixture becomes difficult. So in order to make sure that process of distillation is efficient, you go for azeotropic distillation process. So in this case, what actually we do is we take an azeotrope mixture, and to that azeotrope we add a ternary component. So that ternary component together along with this azeotropic mixture form a heterogeneous azeotropic mixture, and then through the distillation what actually happens is this azeotrope that contains the ethanol is basically deposited at the bottom, and you can actually collect it from the bottom of the distillation column. Whereas in case of extractive distillation, what actually happens is you, again it's the same way, instead you add a ternary component, and that ternary component is actually what it does is it increases the volatility of ethanol. So once it increases the volatility of ethanol, then what happens is the ethanol vapors gets concentrated from the top, and then you can actually get the ethanol separated from the solvent. So these are the two types of distillation process that we actually use in the fermentation. One is the azeotropic distillation and another one is the extractive distillation. Both are almost similar in the process, it's just that their fundamental principle varies. So in case of azeotropic distillation, you add a ternary component, and that ternary component forms a heterogeneous azeotropic mixture, and then the ethanol is separated from the bottom. Whereas in case of an extractive distillation, you add a ternary component, and then that ternary component basically increases the volatility of ethanol, and then it gets removed from the top of the distillation column. So this is about the azeotropic and extractive distillation process. Another way to basically obtain this biodiesel or ethanol from the lignocellulosic biomass is actually through gasification process. There you can get syngas, and then this syngas undergoes a thermal reaction with a particular catalyst to generate ethanol. Or you can get the syngas, and through biological means you can actually produce ethanol. So when you say you use biological means, what I typically mean is you take carbon dioxide as well as hydrogen, and then the microbes feed on these gases to produce ethanol. So the typical microorganisms that usually do this conversion process of syngas to ethanol is belongs to the is known as Clostridium jundahili. I hope I am pronouncing it right. Just a second. Let me just note these points here. So, in case of the biological route, so lignocellulosic biomass, there are two ways to convert them into ethanol. You first take the lignocellulosic biomass and convert it into syngas. And then you take this syngas and then subject it to one is thermal conversion route, or you can say that you basically do a thermal reaction with a suitable catalyst, and the second process is you go for a biological reaction. So in this biological reaction, what you do is you basically use microorganisms, and then feed this microorganism with feed them with CO, CO2 and H2 gas. These microorganisms feed on these gases. These gases are nothing but they are a part of syngas, right? So they feed on these gases and then they generate ethanol. And the microorganisms that is used for converting CO, CO2 and H2 to ethanol, those microorganisms belong to the family of Clostridium, and the particular microorganism that is widely used for this process is called cross Clostridium jungdahili. So this is the particular Clostridium bacteria which feed on the feed on CO2 and H2 to convert them into ethanol. So this is about production of ethanol from fermentation process. Again, apart from that, you also have production of butanol from this fermentation process as well. So any confusion so far here related to what we have discussed? Now we didn't discuss much on this fermentation as far as the week 7 live interaction session or week 7 course content is there. We basically have a revision on what we discussed in the previous session, where we discussed about how to convert starch based waste to ethanol, and in case of the distillation process where you try to concentrate the ethanol, we discussed about two types of distillation process. One is azeotropic distillation and another one is extractive distillation. Apart from this way, the lignocellulosic biomass can actually be converted to give ethanol. The typical way that we follow is we take lignocellulosic biomass and convert them into syngas. The syngas that we get from this process is subjected to two different processes. Either of the way can be used to produce ethanol. So the first process is thermal reaction with a suitable catalyst, and the second process is biological reaction or a biological route. So where we use microorganism to feed upon carbon dioxide, carbon monoxide and hydrogen gases, and then we convert them into ethanol. The microorganism that is typically used for this process is called Clostridium jindali. So next we actually go for ABE fermentation, that is acetone, butanol and ethanol fermentation process. Acetone, butanol and ethanol fermentation process. So we get all these three different solvents through the fermentation process, and from all these three different solvents we try to recover butanol. So what actually happens is we take this lignocellulosic biomass and then we do this fermentation process. For this fermentation process we use two different types of bacteria. One is the Clostridium acetobutylicum and another one is Clostridium beigerin beigerinski. So these both bacterium actually acts on starch as well as that of the lignocellulosic biomass, and it undergoes two different processes. One is the acidogenesis and another one is called as the solventogenesis. So, so let me just write that. Starch, or you can say lignocellulosic biomass, they undergo reaction to give acetone, butanol and ethanol. And how this process happens? It happens using two different microbes. One is the Clostridium acetobutylicum, just a second, Clostridium, and another one is Clostridium beigerin. So these are the two microbes which are used, or microorganisms which are used in this ABE fermentation process. So these two microbes convert the starch and lignocellulosic biomass through acid, acidogenesis and solventogenesis. So in acidogenesis process, what happens is these starch and the biomass waste is usually converted to acid, and in case of solventogenesis, it is basically used for the production of solvents. Acidogenesis is to produce acids. Typical acids is acetic acid and butyric acid, and in solventogenesis process we produce solvents. It produces solvents. So example is ethanol and butanol and acetone as well. So even though butanol is basically produced in this process, there are actually problems related to recovering butanol from the mixture of solvents. So it's not that process is easy process, or butanol recovery is an easier process where you can actually directly extract the butanol. butanol recovery has certain limitations. So typically two major limitations. One is that butanol has butanol has a partial solubility with water. So the partial solubility of butanol with water, what it actually does is it basically makes the recovery process difficult. Second problem is it basically requires high energy equipment. So high energy, since it is partially soluble in water, in order to extract butanol from the mixture of solvents, the energy requirement for this recovery process is going to be intensive. So it's an energy intensive, or you can also say energy expensive process. The butanol recovery process is an energy expensive process. And third thing is so since it's an energy intensive process, so it basically requires high energy equipment, and that development or design of such high machinery equipment for butanol recovery process is still at an infancy stage. So it's still not a very mature technology, so it's still at its infancy stage. So these are the problems that are associated with the recovery of butanol from the ABE uh, solvents. So different processes are used, for example absorption, distillation, uh, then supercritical fluid extraction, pre-evaporation. All those methods are used in order to concentrate the butanol, or basically to recover the butanol from acetone, butanol, ethanol mixture. So, but here comes a question. If ethanol is already being used as a biodiesel, why people actually go on to look for butanol? I mean, are there any limitations with ethanol so that people actually try to use butanol as a biodiesel? Or what's the advantage of using butanol as a biodiesel? We discussed about ethanol and its advantage. So ethanol, since it's actually has carries very since it's environment friendly, and so since it's environment friendly, we use ethanol as a biodiesel. However, one of the major limitations with using ethanol is that it cannot basically produce the amount of energy what you can get from the conventional resources like gasoline. So we try to make a blend out of both ethanol and gasoline, and that is good as a biodiesel. Now, when we have that as a biodiesel already, why is there is a reason to go for butanol? Is butanol, or what are the advantages of butanol as a biodiesel? Does butanol carry more energy compared to ethanol, or produce more energy on combustion as compared to ethanol? Yes, anyone? There should be a particular reason, right, on why we are using certain solvents as a biodiesel, or why there is a look for certain solvent as a biodiesel. Because, as I said, the development of the machineries for recovering butanol is still at an infancy stage. So people have identified something that is interesting, so that they are trying to build equipments or low energy consuming technologies for recovering for recovering butanol. So why, what could be the reason for using butanol, or what are the advantages of using butanol as a biodiesel compared to ethanol? So try to identify, and let's see about this question in the next session. Why butanol is used as a biodiesel? Now we have learnt about ethanol recovery and ethanol as a biodiesel, and butanol and its recovery process, or how it is produced and its recovery process, and why it is used as a biodiesel. Now there is one particular alcohol which is in between ethanol and butanol, that is propanol. So what about propanol? Why we don't talk about propanol as a biodiesel? Two questions. Initially, we discussed about ethanol. So, butanol we discussed, and we discussed that butanol can also be used as a biodiesel. But what are the advantages of butanol compared to ethanol as a biodiesel? That is the first question. Second question is, we are talking about ethanol and butanol, and we have agreed that both can be used as a biodiesel. If so, then what about propanol? So, these are the two questions. So, kindly find the answers for both of these questions. I'm making it I have increased the font size. So try to identify the reason for both, why butanol is used as a biodiesel, and why propanol is used as a biodiesel, or what are the advantages of using butanol as a biodiesel, and what about propanol as a biodiesel. I'll rephrase the question. What are the advantages of butanol as a biodiesel, and what about propanol as a biodiesel? So, this we close our discussion on fermentation. Now we will move towards our discussion on transesterification reaction. How do you basically produce energy through transesterification reaction? So, any idea on what is a transesterification process? So, in case of the transesterification process, what we do is we basically take triglycerides and then react them with some alcohol in the presence of heat and catalyst, so that we can get fatty acids of alkyl esters and glycerin as a product. So, here this fatty acid alkyl esters and then the glycerin is basically used in the biodiesel production. So the typical catalysts that we used are nothing but the base such as sodium hydroxide and potassium hydroxide are used as a catalyst for this particular process. But this has one downside. The major problem is if there is any free fatty acids that are whatever that gets generated from the system, that if any free fatty acids are present, that fatty acids could actually react with the sodium hydroxide or the potassium hydroxide, which basically results to form soap, and that soap actually degrades the quality of the biodiesel that we can obtain through the transesterification reaction. They tend to reduce the energy production or energy efficiency of the uh, biodiesel that we obtain from the transesterification reaction. So this is one of the downfall which you actually need to remember, that is the sodium hydroxide or the potassium hydroxide that is used as a catalyst may react with the free acid if present any, and this particular reaction generates for the formation or results in the formation of soap. The formation of soap degrades the quality of the fuel or the biodiesel that we obtain through the transesterification reaction. Now, how do we get this biodiesel? So what we try to do is we basically take either waste oil or waste oil seeds or the recycled grease from the triglycerides, and then they are actually converted to biodiesel. And for this process we basically go for two different types of techniques. One is the conventional one and another one is the advanced one. In case of the conventional method, we actually use expeller press method and the solvent extraction method. In case of advanced technique, we use ultrasonication method or the supercritical fluid extraction technique. So conventional methods are very simple ones, whereas advanced method uses certain principles for extraction of oil, for improving the oil extraction process from the oil seeds. So in case of expeller press method, it's a simple method, so wherein you take this oil seeds and then you basically press them. So once you put mechanical pressure or mechanical force onto the seeds, what actually happens is the cell wall actually breaks. So once the cell wall breaks, the oil comes out from the seeds. And another one is the solvent extraction method. So in case of the solvent extraction method, what you do is you add a suitable solvent to them. This solvent breaks the cell wall of the oil seeds and leaches the oil out of them, and then you separate the solvent as well as that of the oil through some other appropriate technique, and then you can extract the oil from the seed. So these two process, one of the major problem is that the amount of oil that you can actually obtain through both of these processes is usually limited. So in order to improve upon the yield of the oil that you can obtain from the oil seeds, you actually go for the advanced techniques. So primary reason on why we try to use advanced technique is basically to make sure that we get more amount of a particular product than what we usually get from the conventional method. So this is the typical ideology behind the modifications that we do to the technology. Either it will be for improving the product yield, or it's basically to reduce the energy, cut down on the energy requirement. So basically the major aim is to use less material and get more product, so that the profit margin is more. So that's typically the entire business on why we try to improve a system design. So in advanced method, as far as the biodiesel production or the is concerned, we go for ultrasonication assisted oil extraction process or supercritical fluid extraction. So in case of ultrasonic assisted extraction process, what we do is we subject the oil seeds to ultrasonic wave. Ultrasonic wave is nothing but it's a sound wave. It basically carries energy. So these ultrasound waves break the oil seeds, or you can also say the cell walls of these oil seeds, and then the oil comes out from them. So since you use ultrasonic waves, the amount of oil that you can get from the oil seeds is usually enhanced. So this is about the advanced method and conventional methods. Major reason is to produce more oil so that we can get more, so that more oil can be used to produce more amount of energy. We want to improve the amount of energy that we can produce from this oil seeds. So for that process we go for the advanced techniques, which here is nothing but ultrasonic assisted um, extraction process, and then another one is the supercritical fluid extraction. So majorly this extraction process typically depends on variety of factors. The first one being is the type of the solvent. Then you have the biomass to solvent ratio. So how far you tune this biomass to solvent ratio also affect the solvent extraction process. Temperature. So if you do the process under high temperature, it becomes easy to break the cell walls, so you can get more amount of oil. But care should be taken, what is that the temperature that you use for the process should be lower than its boiling point. It makes sense, right? If you heat the oil seeds at a temperature greater than the boiling point of the oil that you are going to extract from that, so as the oil keeps going coming out, the oil will start vaporizing. So you will not be able to get a higher yield. So the temperature that we use for this solvent extraction process has to be optimized, where we use a temperature below its boiling point, but at the same time we need to improve upon the extraction of oil from the seeds. And then the other factors is the extraction method plus time, because more the time, more will be the extraction of oil from the seed. Then the moisture content, particle shape, and as well as the size. So once we obtain the biodiesel, we usually characterize them. So we characterize through different process or through different methods. So there are several um, methods through which we characterize the biodiesel, or you can say the several parameters through which we characterize the biodiesel. So we have the cloud point, then we have something called pour point, fire point, flash point, heating value, iodine value, ash content, percentage of sulfur and phosphorus, and then you have you try to determine the free fatty acid content in the samples. So all these points are there, so we will discuss about them, but we will discuss that through the question and answers, or you can say the MCQ questions that we will discuss now. So any questions related to so far what we have discussed on transesterification and fermentation, or any confusion, any doubts? So I have given a gist of what has to be discussed for week 7 live interaction session or week 7 course content. So so in case if any of you have not watched the video lecture, so I encourage all of you to go and have a detailed understanding on each of these process. What we discuss here is just a quick summary, but the course content deals much greater in depth. So please have a look at the video lectures that are uploaded in the website. Any questions on fermentation and transesterification process? Anyone? Or shall we move ahead with the problems that we have for today? So let's start with the problems. Just in case if you have any doubts, you're welcome to ask me. But let's look at the questions one by one. So, first question: which of the following is a relative measure of the interval between the beginning of injection and auto ignition of fuel? Which of the following is a relative measure of the interval between beginning of injection and auto ignition of fuel? So these are the parameters by which you actually characterize the biodiesel. So as I just now we discussed, we will be discussing about each of these points and some more points that are not covered in our discussion before. So if you know the answer, please let me know. Which of the following measure is a which of the following is a measure of the interval between beginning of injection and auto ignition of fuel? Any answers? Which of the following is the relative measure of the interval between the beginning of injection and auto ignition of fuel. So the answer to this is cetane number. So So cetane number actually measures the interval between the beginning of injection and the auto ignition of the fuel. So higher the cetane number, it actually means that the time between the injection and the auto ignition of the fuel is short. Faster ignition of the fuel happens if you have a fuel with a higher cetane number. Now, if this is cetane number, what is octane number, pour point, and cloud point? The definition. This definition is there in the course content as well. So, octane number, pour point, cloud point. Octane number. When we characterize whether a particular fuel or a diesel or a biodiesel is suitable for the what do you say, is suitable for the ignition process, or is whether that particular solvent is a suitable fuel for internal combustion engine or for combustion or for internal combustion engine, then we have to look at octane number, cetane number, pour point, cloud point, fire point, flash point. Then we have to discuss about the moisture content as well, their percentage of sulfur, phosphorus in them. So all these parameters we need to have an understanding. So these parameters forms like a checklist to basically determine whether a particular fuel is a good fuel for, or whether a particular solvent can be used as a fuel for the internal combustion engines. So we need to have an understanding on each of these parameters. What are their parameters? What is its definition? And whether having a particular value, or whether having a higher cetane number or a higher octane number is good for the solvent to qualify as a fuel. or to qualify as a good fuel for the internal combustion engines. So octane number, anyone? Any idea on what is octane number? So octane number is nothing but it is a measure, or you can say it is the ability, or you can say it's the ability of the fuel to resist or withstand compression in the internal combustion engine. So this is what is the known as octane number. So again, this is a definition, so you need to remember them. So now tell me whether having higher octane number is good, or whether having low octane number is good. Now you know the definition of octane number. So in order for a particular solvent to qualify as a good fuel, should it have higher octane number or lower octane number? Which is better, higher octane number or lower octane number? Which is better for a particular fuel, higher octane number or lower octane number? Always higher octane number will be good, because that will have the ability to resist or withstand the compression, and basically have a resistance towards the premature ignition that can happen in the internal combustion engine. Now cetane number we already discussed. What's a pour point and cloud point? Pour point, cloud point. So pour point is nothing but it's basically the temperature at which the fuel, or you can say at which the oil starts to flow, and cloud point is basically the temperature at which the oil appears to have a cloudy, or you can say, and which the oil has a cloudy appearance and begins to solidify. So if I write this, pour point is nothing but it's a parameter relating to the temperature at which the oil starts to pour easily or flows easily. And a cloud point is basically the temperature at which oil has cloudy, or oil begins to have cloudy appearance and tends to solidify. So when you reduce the temperature of the oil at one particular temperature, as you keep cooling it down, above the surface of the oil, you can actually see a cloudy appearance. So beyond, if you decrease the temperature, the oil starts to solidify. That temperature is called as a cloud point. And there will be another temperature where upon increasing the temperature, the oil's viscosity will decrease and it will starts to flow. That temperature is called as pour point. So any temperature below the pour point, the oil will remain as solid, or the flow of the oil will be ceased. So that is pour point. Now you know what is pour point and cloud point. So tell me, which temperature will be higher? Is it the temperature at pour point or the temperature at cloud point? Which temperature will be higher? Is it the temperature at pour point or temperature at the cloud point? Which temperature is higher? Pour point temperature or cloud point temperature? Check at the definitions and then I think you will be able to make uh, you'll be able to come up with an answer. So try to identify. So this question also I'm going to give it as a task. Which point is, or the temperature of which of the following is greater? Is it the pour point or the cloud point temperature? Now let's move on towards the next question. The acid value is calculated as. So one of the ways to actually determine the percentage of free fatty acid that is present is usually through the acid value. Now we have to say how we actually determine the acid value. What's the formula? And of course, you need to define to me what are the parameters V, C, and M. What's the acid? I mean, the acid value is calculated as among the four options. Which of the following is correct? And describe the variables V, C, and M. Anyone? This is a straightforward question. So I hope all of you are going through the course slides. If you want, you can actually type in your answers. You don't need to actually unmute yourself, and then you can type your answers in the chat box as well. The acid value is calculated using which of the four options? So it's option C. Now, here what is V, C, and M? as well as what does this 56.1 determines or signifies. So V represents for the initial, oh, so V represents for the initial volume of KOH. C is nothing but it is the concentration of KOH. M is the, what is M? Mass of the sample for analysis. And the 56.1 represents the molecular weight of KOH. Just a second. 56.1 represents for the molecular weight of KOH. Just a second and just make this. So the acid value is usually the acid value is to determine the conversion of the free fatty acids in the transesterification process. There, the value is usually determined as 56.1 times V times C by M, where V is the initial volume of KOH, C is the concentration of KOH, M is the mass of the sample for analysis, and 56.1 represents for the molecular weight of KOH that is used. I hope these two questions there are no doubts except for the one question that I asked, at which point the temperature will be greater, pour point or cloud point. If you have any questions other than this, let me know before we progress towards the next one. The next question is the figure below, or this what does this figure represents? Any questions related to this first two MCQs? So, what would be the answer for the third one? So you see this figure in the at the right corner, right bottom corner. What does this figure represents? This figure is typically for the extraction of butanol, or you can say the recovery of butanol, but we need to describe through which particular process do we recover this butanol. Is it gas stripping process, supercritical fluid extraction, liquid extraction, or pre-evaporation? In case if you don't remember, then you can refer to the course slides now and then let me know the answer. Because this is there exactly in the lectures. So the main purpose of this live interaction session itself is to revise what we have what we learned during the video lectures and get the doubts cleared and to discuss more questions, similar questions as of your assignments. So you can refer to your lecture notes and then let me know what is the answer for the third question. Which of the following recovery process, butanol recovery process, does the following figure represents? So try to identify the answer for this one. I am not going to give because this is directly from the course slide. So let's move on towards our next question. Which of the following is defined as the amount of ethanol produced per unit of the substrate utilized per unit time? Is it ethanol yield, ethanol productivity, or maximum theoretical yield, or none of this? Which of the following is defined as the amount of ethanol produced per unit substrate utilized per unit time? And of course, give the mathematical expression as well, because that will be important when we calculate or when we go for solving problems related to the calculation of ethanol yield, ethanol productivity, and maximum theoretical yield. So how do you define ethanol yield? Based on that, we can actually build up on what is ethanol productivity and what is maximum theoretical yield. So the answer for this is ethanol productivity. And as I asked for the mathematical expression, let's start from the ethanol yield. Ethanol yield is usually given by yield of ethanol I'm just writing the mathematical expression CV by M, where C is nothing but concentration of ethanol, V is the initial volume, and M is the mass of the substrate. So ethanol productivity, which is defined as Q, you can relate this as 1000 times ethanol yield by T. Again, ethanol yield we discussed before in the previous option. Here T is nothing but the time at which the ethanol concentration ethanol concentration produced by the substrate is maximum. So this is the definition of ethanol productivity. That is the amount of ethanol that can be produced per unit substrate per unit time, where the time is nothing but it's basically the time at which the concentration of the ethanol that is produced by the substrate is maximum. Now comes the maximum theoretical yield that you can actually obtain. So for every process, if you see, you have something called as a theoretical yield, which is nothing but the maximum amount of product or the ethanol that you can obtain from a particular process. But usually the theoretical yield remains greater than what you can actually get. Of course, for every system or every process that you use or that you develop, there will be certain limitations, or you can say there will be losses which actually pull down the yield lower than the theoretical yield. So, theoretical yield is usually defined as ethanol produced in sugar times 100. That 100 is for calculating it in terms of percentage, divided by initial sugar in reactor times 0.511. So this is how you calculate the maximum theoretical yield, or you can say maximum theoretical yield of ethanol. Now, what does this 0.511 actually represents? Because knowing formula is important, but what is actually more important is to knowing what are the parameters that are involved in the formula. So that is the reason we typically, we usually see what does each variable over there represent. So here, ethanol produced from the sugar and initial sugar in the reactor we know. But what does this 0.511 actually represents? Produced in, I already produced from. Anyone, what does that 0.51 factor represent? So it typically represents the number of moles of ethanol that will be produced for every mole of glucose unit. So for 1 mole of glucose, if you take, how much moles of ethanol that can be produced, the stoichiometric uh, coefficient. So for every 1 mole of ethanol, 0.51, sorry, for every 1 mole of glucose, 0.511 mole of ethanol will be produced. So that is this 0.511 here represents the number of moles of ethanol that can be produced from 1 mole of glucose. So any doubts related to the four questions that we discussed? The next two questions will be pretty easy because we have discussed this. So if you have anything to discuss related to the three or four questions that we discussed so far, please let me know, or otherwise we can go for the next two questions. So let's move on towards the next question. The next question is, the biological route uses which of the following bacteria for ethanol production from lignocellulosic biomass or lignocellulosic waste? Is it cyanobacteria or bacillus or clostridium jungdehli or none of this? We discussed this right, I mean, at the start of this class or of this live interaction session. Anyone? So it's Clostridium jungdehili, right? Because we discussed this right now. So let's move on towards the next question. Which of the following catalyst is used in the transesterification process? Is it sodium hydroxide, potassium hydroxide, magnesium sulfate, or both A and B? So it's both A and B, right? As we discussed in transesterification process, we basically use catalyst, and that catalyst is usually a base. So either sodium hydroxide or potassium hydroxide. That's where we discussed that if you have any free fatty acids that is present, these free fatty acids can actually react with these bases that is used as a catalyst to form soap, which actually degrades the quality of the fuel that we produce through, that gets produced through the transesterification reaction. So here the answer would be both A and B, both sodium hydroxide and potassium hydroxide. So let's move on towards the next one. I hope no one has any questions to ask. If you have any ambiguity or if you are facing any difficulties with respect to the questions that we discuss now, please feel free to speak out here, or you can also post your queries in the chat box. So let's move on towards the next question. Match the following feedstocks with their catalyst used in the production of biodiesel. You have sunflower oil, soybean oil, babasu coconut oil, and then you have the catalyst for them. So we need to match which feedstock or which catalyst will be suitable for which feedstocks for the production of biodiesel. So just a second, so you can assume it this way. This is 1, this is 2, this is 3, this is P, this is R. Yes. So the answer is it is 1R, 2P and 3Q. So this is a straightforward question. So please have a look at the course content, the slides of the lecture. So this is a straightforward question where you use sunflower oil, and in order to extract biodiesel or in order to produce biodiesel you use SRO as a catalyst, and for soybean oil you use K2CO3 or TiO2, and for babasu coconut oil you use amberlis 15, which is a sulfonated ion exchange resin. So next question is, what are the methods used for sulfur detection? Is it colorimetric method, big bond combustion, X-ray fluorescence or XRF, or all of the above? Which of the methods is used for sulfur detection? Colorimetric method, big bond combustion method, XRF, or all of the above? When I say sulfur reduction, I actually mean to quantify the percentage of sulfur in the biodiesel or any kind of fuel that you have. Here it is biodiesel. So which of the following method is used for the sulfur reduction in biodiesel? Colorimetric method, big bond combustion method, XRF, or all of the above. So it is all of the above. Both for for sulfur reduction, we basically use all the three methods, and the other method apart from the above three is the ICPMS, also called inductive coupled plasma mass spectrometry. So there you actually try to analyze the elements with respect to their mass, and for that you actually use plasma. So ICP-MS technique is also used for sulfur reduction. Let's move on. We will end our session with these three questions. So the next question is: the most common and traditional microorganism used for fermenting sugar into ethanol is called. The biological name of that. It's also called yeast actually. Common name is yeast. What is the scientific name for yeast? So it's called sacro. myces, oh sorry, cerevisiae. Saccharomyces cerevisiae is the common traditional. Am I writing the spelling correct? No. So just check the spelling, Anu. But the name is Saccharomyces cerevisiae. So that is the most common microorganism that is used for fermenting sugars into ethanol. Next, match the following columns. You have four different types of sugar. You need to match it with their molecular formula. So first you have glucose, cellobiose, xylose and xylobiose. This should be a simple one. So I'm expecting answers. Glucose, cellobiose, xylose and xylobiose. And their molecular formula, you have pentose sugar, hexose sugar, then you have C12H22O11 and C10H18O9. So what is for glucose? Leave about xylose, cellobiose or xylobiose. Glucose we know. We wrote the reaction also in the last live interaction session. Glucose is a hexose sugar, right? So among the following hexose sugar, when I mean it should have 6 carbon. So the only option that has 6 carbon is C6H12O6. That is yes. So glucose is just one is S. Now, if you join or if you link two glucose units, you get a cellobiose. So C6H12O6 plus C6H12O6, when you link both of them, you have C12H22O11. So that is cellobiose. So 2 is R. So just write, let me write it somewhere. Cellobiose is 2 units of glucose linked. Now we have xylose. So xylose is a pentose sugar. So 3 will be Q. And we have xylobiose. So similarly like cellobiose, xylobiose is, xylobiose is nothing but 2 units of xylose, or you can also call that as arabinose linked together. Arabinose. So kindly remember this, because glucose, xylose, we may have an understanding that is a pentose sugar or a hexose sugar, but this cellobiose and xylobiose is nothing but the 2 units of glucose or 2 units of xylose are also called as arabinose. When they are linked together, we call them as cellobiose or xylobiose. So fourth one will be 50. Now, let's move on towards the next question. I think this should be simple. The microorganism ingests carbon monoxide, carbon dioxide, and hydrogen and mostly produce what? Butanol and water, biogas, sugar and alcohol, ethanol and water. We just discussed this is about that I think the answer is there in the previous question itself. It's based on that bacteria Clostridium jundahili. Anyone with the answer? Okay, so I'll show the this thing. So this one for ethanol production from lignocellulosic biomass and waste. So based on that, the answer should be ethanol and water. So any doubts related to what we have discussed so far? Any questions you have? Because I'm going to stop the session for today here because I don't think there is any time as well as time left for today's discussion and any questions? Sorry. Any questions or shall we conclude the session for today? So if you have no questions, then I think we can conclude our session for today. So thank you all for joining today's live interaction session, and I thank Professor Prasenjit Mondal sir as well as the NPTEL team for providing me this opportunity to interact with you all on this Sunday afternoon from 5 p.m. to 7 p.m. Our next live interaction session will be on 15th of March. That will be our last live interaction session for this course. So over there, so probably in the next week, we may not be looking at the concepts like how we discussed it today. We will we will straightforward, we will actually go towards the problems and the multi-choice questions that we have. So I think that would be the plan, that would be the appropriate plan for next week. So if you have any questions, you are welcome to post that in the group or email it to me. I'll be able to respond to it as soon as possible. So thank you for joining today's live interaction session, and I hope to see you in our last live interaction session next week. So thank you and have a great weekend and a great week ahead. Thank you and bye.